Why is nonlinear damping modeling so complex? Imagine trying to predict how a swing moves when you push it harder or softer. Now picture doing that for a machine part that vibrates in unpredictable ways. That's what nonlinear damping modeling is all about. It's a puzzle that keeps engineers on their toes because it doesn't follow simple rules. In most basic cases, damping is like a gentle brake that slows down vibrations in proportion to how fast something is moving. That's called linear damping. But real-world systems often don't behave that way. Instead, the damping force can change depending on how big or small the vibrations are, or how fast they happen. This is called nonlinear damping. It's like trying to catch a ball that sometimes feels heavier or lighter depending on how you throw it. One big reason this gets complicated is because the damping force depends on the vibration amplitude. If the vibration is small, the damping might be weak. But if it gets bigger, the damping could suddenly become much stronger or weaker. This means you can't just use one fixed number to describe it. Instead, you need to figure out how the damping changes as the vibration grows or shrinks. Another challenge is that the system's response to vibrations isn't always straightforward. If you push a system with a steady, smooth wave, it might respond in a predictable way. But if the vibrations are random or very complex, predicting what will happen becomes tricky. The shape of the vibrations can change, and the energy loss doesn't follow simple rules. To understand this, engineers have to use advanced math and run many calculations. The process of modeling also requires iterative calculations. Because the damping depends on how the system responds, and the response depends on damping, you need to keep adjusting your model over and over. This feedback loop makes the calculations more time-consuming and demanding. It's like trying to tune a musical instrument that keeps changing its tune every time you adjust it. Plus, real systems have many sources of nonlinear damping. Friction between parts, material hysteresis, where materials don't return exactly to their original shape, joint slip, and fluid structure interactions all contribute. Each of these mechanisms has its own mathematical way of behaving, which makes creating a single model that covers everything very difficult. There's no one-size-fits-all model for nonlinear damping either. Engineers often use simplified or approximate models to get close to reality. But these models rely on assumptions that might not hold true in every situation, especially when vibrations are large or unpredictable. This makes it even harder to get accurate predictions. Finally, figuring out the parameters for these models through experiments is a challenge. It's tough to separate nonlinear damping effects from other nonlinear behaviors in the system. Engineers need sophisticated testing methods that analyze vibrations in time and frequency domains. These tests can take a lot of time and requiring careful interpretation. Understanding and modeling nonlinear damping is essential for designing safer, more reliable machines and structures. It helps predict how they will behave under real-world conditions, which can prevent failures or improve performance. But the complexity comes from the fact that the forces involved change with vibration size and speed, requiring advanced math and many calculations. That's why nonlinear damping modeling remains a challenging and fascinating part of vibration and acoustic studies.